Alright, it's time for the last section of solutions, and that is going to be solution stoichiometry. So this is the same general procedure. We're using conversion factors to change from one unit to the other. We use a balanced chemical reaction to go from the amount of one thing to amount of a different thing, a product versus a reactant. So in the past, though, we've always done grams to moles to moles to grams. You've heard that same mantra over and over again. The problem with solutions is when we have solutions, we start with things like 50 milliliters of a 0.1 molar solution. How does that tie in with this? How do we go from a solution to moles to grams? And that's what we're going to talk about in this unit. So let's make a trip back to Mole Island. Now, if we think of this Mole Island thing, we dealt with mass to moles to moles to mass. So that's the grams to moles to grams that we've been doing over and over again. We're going to have to take a different route here now because we don't start with mass when we have solutions. We start with volume. So now we're going to go from volume to moles to volume. And then particles, that's just Avogadro's number, so we can make that process if we wanted to, but we very rarely deal with particles anymore. With solutions, we're going to have to go from volume to, not usually volume because we're dealing with a precipitate. A precipitate's a solid, so we can get the mass. So the most common flow here is going to be from volume to moles to mass. And the way we would get from volume, so the amount of solution that we have, to moles is using molarity. So molarity is big M and it's moles divided by liters. So what it tells us then is it tells us the number of moles for every liter of solution. Moles per liter, why, that's a conversion factor. And so that means if we have something like, let's say, we have a 10 molar solution. That is the same thing as saying 10 moles for every 1 liter. And then we can use the amount of liters we have to convert from volume, which is liters, to moles. And then we can go from moles to moles just like normal, and from moles to grams just like normal. So if you still have your Mole Island notes from back when we first started talking about stoichiometry, this does look a little different. When we talked about volume back then, we talked about it in terms of gases. Now we're going to talk about it in terms of solutions. And so to go from volume to moles, we would use molarity, which is the moles for every 1 liter. So for example, let's say we have 0.1 liters of a 2 molar solution, or 0.2 molar solution. Okay, so we have 1 liter, 0.1 liter of a 0.2 molar solution. How many moles is that? Well, we have 0.1 liter, that is our given, and we know that there is 0.2 moles for every 1 liter. Liters can go ahead and cancel out liters, and that tells us that there is 0.02 moles. Now, if this was an actual stoichiometry problem, you'd be given something to convert to, and so you would use this volume to moles as step 1. Then from moles to moles, you'd use the balanced equation, and then from moles to grams, you would just use the molar mass from the periodic table. All right, so let's practice. We have a balanced reaction here with silver nitrate and sodium chloride, producing silver chloride and sodium nitrate. So in this case, I've labeled the phase of matter already. We can see that silver chloride is a solid. In the future, now that we know our solubility rules, we have that list, you should be able to predict who the precipitate's going to be, so what the different phases are going to be on the product side. Question is, how many grams of silver chloride can be produced from 25 milliliters of 1.5 molar silver nitrate? All right, so kind of a struggle that people run into here is a lot of times they'll see these two numbers, so 25 milliliters and 1.5, and they'll start with the wrong one. So you have to figure out who is your starting number, what is your given. 1.5 molar, that right there, that is a conversion factor. It is 1.5 moles per liter. You never start with a conversion factor. You always start with a single number by itself. And so in that case, we're going to be using that 25 milliliters as our starting point. But we can't use milliliters, it has to be in liters. So let's convert that over by moving the decimal over 3 places. So 0.025 liters of silver nitrate. And now is when we use that molarity. So we know there is, from this guy right here, that's our conversion factor, we know that there is 1.5 moles of silver nitrate for every 1 liter. That makes it so that liters will cancel out liters. Okay. So we have gone from molarity to moles, and now we go to moles, and we just follow that old normal path. Look up at the balanced equation, and there is 1 mole of silver nitrate for every 1 mole of silver chloride, and so it's going to be 1 mole for every 1 mole. And I'll go ahead and label the units on those. And now we can see that moles of silver nitrate cancels out moles of silver nitrate, and we can go to that final step of grams. And so 1 mole of silver chloride, we can look on the periodic table, add up 1 silver, 1 chloride, and get 143.2 grams of silver chloride. And then moles cancels out moles, and we're left with grams, so we can solve that guy out. When we do that, go ahead and type it into your calculator and check your answer. You should get 4.3 grams of silver chloride. And that's taking into account significant figures, since this number and this number both have 2. Our answer can only have 2. So there you go. That was your first solution stoichiometry problem. Only thing different between this and any other stoichiometry problem is this first step of going from volume to moles. And we just used the molarity to figure that out. All right, here's another practice problem. This one's a little bit different. It deals with lead nitrate and potassium iodide, producing PbI2, so lead iodide and potassium nitrate. You can see this is a solid. We should also know that from our solubility rules. Question is, how many grams of PbI2 can be produced from 115 milliliters of 0.5 molar potassium iodide? So there's our conversion factor. There's our starting number. And once again, we're assuming excess lead nitrate. When I say that, all I mean is there's plenty of this. We're not going to run out with it. It's not a limiting reagent problem. Hey, so if you think you get it, and most of you probably should, go ahead and pause the video, give this one a shot, then resume to check your answer. Welcome back. I'll buzz through this one pretty quick for those of you who are checking your answer, and those of you who are following along at home should be able to see what I'm doing. So we have 115.115 liters of our solution. Let's call it solution. And there is 0.50 moles for every 1 liter of solution. And that is moles of Ki. Okay, and liters of solution cancels out liters of solution. So liters of solution is a better label than liters of potassium iodide. And then if we look up at our balanced equation, there's 2 moles of Ki for every 1 mole of lead iodide. So we're going to have 2 moles of Ki on the bottom versus 1 mole of PbI2 on top. Cancel, cancel. And last but not least, that molar mass step is 461.0 grams for every 1 mole of PbI2. And cancel, cancel. All right, we are good to solve now. And so when we type that in, multiply and then divide by 2, we should get with sig figs 13 grams of PbI2. Okay, so that was another one very similar to the first one. So this is a kind of pretty good indication of the type of problem we're going to be asked with these. A lot of times you're going to be needing to identify what the solid is, though, in order to figure these out. Sometimes you'll have a limiting reagent problem. So stay tuned for another practice problem here on the next slide, and that one is going to be a little bit trickier. Haha! On this one, you are not given a pre-written, pre-balanced equation. You're going to need to do it yourselves. So we should know how to name our ionic compounds or get formulas from them. We should know how to balance reactions, and all of these are just going to be partner swapping when we write them out. Then you also need to identify who is the precipitate. So this question is saying we have 25 milliliters of 2 molar sodium carbonate, 25 milliliters of 2 molar iron 3 sulfate. How many grams of precipitate can you form? What's the precipitate? Well, first we've got to write out the reaction, label the phases, and then we can figure out who the precipitate is, because it will be the one that is insoluble, which means it will be the solid. Hey, give this a shot. So pause the video, try writing this equation. You should be fairly familiar with this, fairly comfortable with doing this by now, and then resume the video to check your equation. This is going to be something you're going to have to do quite often during this unit. All right, so here is the written and balanced equation. So it's balanced for charges and for atoms. Okay, so we've got the same number of sodiums on each side, irons, all of that. Charges are balanced, so the 2 minus on carbonate is balanced out with the 2 of the pluses of sodium. Now to label the phases. So when we label phases, the reactants are always aqueous. They should always be aqueous. We can't combine them if they're solids. They won't double displace if they're not aqueous. So both of those should be soluble. Over on the product side, that's where we've got to figure out who the precipitate is, if there's a precipitate formed at all. And in this case, there is. So remember that sodium and all group 1 metals are always soluble, so you should look at this guy right here. Don't even have to look at your solubility rules. You know that since there's a group 1 metal there, it is instantly aqueous. Now, if you look at your solubility list, carbonates are generally insoluble, except when they're with ammonium and other group 1 metals. And so this one is going to be our solid. So when it talks about precipitate, they're talking about the iron carbonate. Now, if you look at the question, we have 25 milliliters of 2 molar sodium carbonate and 25 milliliters of 2 molar iron 3 sulfate. We have 2 ingredients here of different compounds. What does that mean for us? Let's say it together. It means limiting reagent problem. So we're going to do 2 stoichiometry setups here. Look at our 2 answers. Whichever one is smaller is the one that is correct. The one that's larger, that's in excess, and we can go ahead and cross that out because we'll never use that number again. Pause the video, give both of those a shot, then resume the video and check your answers. All right, so here is my first ingredient. So that does, believe it or not, spell sodium carbonate. And then I solved out the sodium carbonate solution right here. So if we had 25 milliliters, that's 0.025 liters of a 2 molar solution, which means 2 moles for every 1 liter. I shortened it so I could fit it onto one page. NaC, that's sodium carbonate. FeC, that's iron carbonate. And so when you see those on there, that's all that means. So when we write it like this, that means liters of solution cancels out, moles of sodium carbonate cancels out, moles of iron carbonate cancels out, and we're left with grams of iron carbonate. And so from 25 milliliters of a 2 molar solution, we can produce 4.86 grams of iron carbonate. Okay, but that wasn't the only ingredient, so that isn't necessarily the right answer or the final answer. We need to do the same thing, but this time we're going to do it with the iron sulfate as the starting ingredient. Once again, go ahead and pause the video, and you can try that one, or you can just wait a couple seconds if you've already done it, and it'll pop up here. And there it is. So once again, we've set it up very similar in process. Liters of solution cancels out liters of solution. I used FeS to represent iron sulfate. And so moles of iron sulfate cancels out moles of iron sulfate. And this is a 1-to-1 ratio because of a balanced equation. So moles cancels out moles. And we can now solve for grams as 14.6 grams of iron carbonate. So if we compare these 2 numbers, from sodium carbonate we can produce 4.86 grams. From iron sulfate we can produce up to 14.6 grams. But if we can only make 4.86 grams of iron carbonate from the amount of sodium carbonate we have, well, then we can't make all the way up to 14.6 grams. We will run out of sodium carbonate, which means that sodium carbonate is our limiting reagent and iron carbonate is in excess. I'm sorry, sodium carbonate is the limiting reagent. Iron sulfate would be in excess. All right, so that is solution stoichiometry. Not vastly different from any of the other stoichiometries that we did. Just in this case, we have molarity for our initial step. And then we still have the limiting reagent stuff thrown in there. You still need to be able to know your solubility rules and write and balance equations.